Now let's look at one more topic on probability, and this section really has to do with counting. So we've seen counting a bit, particularly at the beginning of this chapter, on different ways that we can count and some formulas there, but there actually are more formulas that we can use in addition to this for more complicated problems. So let's look at some of those. So we see first the idea of permutations. So an important application of the fundamental counting principle, which we saw way back a few videos ago, which is used to find the number of ways two or more events can occur in sequence, is determining the number of ways n objects can be arranged in order. An ordering of n objects is called a permutation. So a permutation is an ordered arrangement of objects. The number of different permutations of n distinct objects is what we call n factorial. So that's an exclamation point. In math, that is called a factorial. And basically what it does is it allows us to multiply down. So for instance, as an example, 5 factorial is 5 times 4 times 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so going all the way down the line, that's what a factorial means. And that is a fast way for us to figure out the number of permutations. So let's look at an example. So the objective of a 9x9 Sudoku number puzzle is to fill a grid so that each row, each column, and each 3x3 grid contains the digits 1 through 9. So if you haven't seen Sudoku yet, you can sort of check it out. I'll just actually show you a quick picture from our textbook right now. So it looks like this. So you have 9x9, and then you also have these 3x3 squares within it. So what you want to do, the goal of the puzzle, is to use the digits 1 through 9, and you have to find a way to place every digit 1 through 9 in each row, each column, and within each 3x3 grid without repeating them, so that each of these things only contains the digits 1 through 9. And they're pretty fun puzzles. If you haven't checked them out yet, let's take a look at it. So we want to know how many different ways can the first row of a blank 9x9 Sudoku grid be filled in. So here we have some numbers filled in. So we're not talking about this. We're saying, let's say the whole row was blank. How can you arrange the different digits 1 through 9? How many options are there? Now, without even thinking about factorial for a second or the formula, if you have your digits, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and you're using the digits 1 through 9. Well, each of those digits can only be used once. So in the first square, you have 9 choices here, right? So you can put the numbers 1, 2, 3, 4, 5, 6, 7, 8, or 9. So you have 9 choices. Well, in the second square, then you only have 8 choices because we're not going to repeat factors. They can only be used once. And then here you would only have 7 choices left, 6 choices left, 5, 4, 3, 2, and 1. So you can actually kind of see where this idea of the factorial is coming from here. If we think about just our choices for the squares, we can see the factorial appearing. So you have, multiplying this all together, this many combinations here. So if I have 9 different options, then my answer for the different ways that we can arrange those options would be 9 factorial. And if you multiply that out, you get 362,880. So quite a lot of different ways that we can arrange 9 numbers, right? Okay. And then here also order does matter. So we are including the order here, right? So order does matter, which is important to note here. So the combination, 9, 8, 7, 6, 5, 4, 3, 2, 1 is different than 1, 2, 3, 4, 5, 6, 7, 8, 9. So we are allowing for the fact that order is important in making distinct permutations. Now we can get a little more complicated than this. So you may want to choose some objects in a group and put them in order again. Such ordering is called a permutation of n objects, taken R at a time. So we have this formula here. Again, it's a little bit more complicated. This is our notation. And here's a great example. Find the number of ways of forming 4-digit codes in which no digit is repeated. So again, you have 1, 2, 3, kind of 4 boxes here. And what happens is you have the digits. So you're using digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. So you have 10 options for digits that you can use within those 4 boxes. So we're going to choose just 4 there. So the notation is 10p4. So we have 10 options altogether. We're looking at permutations in this case. So again, different ways that we can arrange those numbers where order matters, right? So if you're thinking about a code, 3216 is different than 6312, right? Even though there's the same numbers, the different ordering is a different code. So the ordering does matter. And we're choosing 4 of the 10 options. So using our formula, we have, well, our n here is 10. So we have 10 factorial. And then we have 10 minus r is 4 here, factorial. So you're looking at 10 factorial divided by 6 factorial. 10 minus 4 is 6. Now, think about what's going on here. This means 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. And 6 factorial is 6 times 5 is 4, 3, 2, and 1. So you actually see a lot of times when we use this formula, we do have some values that cancel out, right? So we can simplify this before we start multiplying. Sometimes you do need to do this. Sometimes factorials can get so large that you actually do really need to multiply and cancel things out first. So when we multiply what's left over, all we really have is 10 times 9, 8 times 7, which ends up being 540. Now, you probably could have also figured that out just by using a counting technique. So if you think about here, if I would have 10 options, well, my first box would have 10 options. Then I'd have 9 digits left to choose from, 8 digits, and 7 digits. So you actually can see the result right here without using the formula, just kind of thinking through your options. So that's another way to do it. Just whatever works better for your brain is fine. Here, each year, 33 race cars start the Indianapolis 500. So we have a total of 33. How many ways can the cars finish first, second, and third? So we're looking for specifically an arrangement of 3, right? So first, second, third would be 3. So what we're looking for here is 33, choose 3. So we have 33 cars and we're choosing 3 for that first, second, and third place. And again, the ordering does matter, right? So what we have here is 33 factorial over 33 minus 3 factorial. Well, 33 minus 3 is 30. So what ends up happening here is you have 33 times 32 times 31 times 30 times 29 all the way down to times 1. And in denominator, you have 30 times 29 all the way down to times 1. So what's going to happen is most of your values are going to end up canceling, and you're really going to end up having a few of them left in the numerator here. So 33 times 32 times 31 is 32,736.